Chapter 1: The Discovery That Transformed Reality. Imagine yourself aboard a spacecraft, accelerating steadily toward the speed of light. Your wristwatch keeps marking every second with perfect calm, ticking away as though nothing extraordinary were happening, while outside the window, Earth drifts farther and farther into the distance. Hours stretch into days, days into weeks, and weeks into full years. And once your velocity reaches 99.9% of the speed of light, something astonishing occurs. Every single day you live corresponds to 2 entire months passing on Earth. But then comes the question capable of rewriting your understanding of the universe. What would happen if you reached the speed of light exactly? The answer overturns everything we believe we know about reality and about the nature of time itself. Tonight, on Deep Space Comm, we dive into one of the deepest enigmas humanity has ever faced: the intimate connection between velocity, time, and existence. You are invited to step into a scientific journey that may permanently reshape your perception of the cosmos. And if you enjoy discovering the universe's hidden secrets while winding down at the end of the day, consider yourself part of our nocturnal community of cosmic explorers. And join us by subscribing so you never miss the next voyage into the unknown. What would you think if I told you that everything you believe you understand about time is an illusion? What if you learned that a young physicist, only 26 years old, discovered that time can slow down, speed up, and even come to a complete stop? In 1905, Albert Einstein did more than revolutionize physics. He redefined reality itself. Let us travel back for a moment to the world of 1905. Isaac Newton had crafted a universe that resembled a flawless celestial machine, a realm where time flowed like a steady, unbroken river. For more than 2 centuries, this vision of absolute time served as the foundation of all science. Time was universal, immutable, identical for everyone in the cosmos, without exception. Suggesting that time could vary its rhythm would have been considered pure madness, and yet Einstein was about to demonstrate that sometimes those called mad are the ones who see most clearly. The implications of questioning the absolute nature of time were monumental. If Newton was wrong, then our entire understanding of the cosmos, from the motion of planets to the fall of an apple, would have to be rebuilt from its very foundations. Humanity confronted the terrifying possibility that its most fundamental conception of reality was deeply mistaken. Einstein was manipulating the pillars of existence itself. Everything began with what appeared to be a simple obsession: light. Since childhood, Einstein had wondered what he would see if he could travel exactly alongside a beam of light. Would the beam appear frozen? Would the entire world stop around him? These seemingly innocent questions contained the seeds of a scientific revolution unprecedented in human history. The 1887 Michelson-Morley experiment had created a puzzle that baffled physicists of the time. Scientists expected the speed of light to change depending on Earth's motion through space. Instead, they found something that seemed impossible. The speed of light was exactly the same in every direction. It was as though the universe itself were conspiring to preserve this cosmic speed limit, no matter how or from where it was measured. Einstein realized that the answer required a complete transformation of perspective. If the speed of light was constant in all circumstances, then something else had to change: time itself. This revelation was so radical, so revolutionary, that even Einstein initially doubted it. He was proposing that time, the most intimate, personal, universal experience shared by all humans, was not what it seemed. But the mathematics was merciless and undeniable. Einstein's equations revealed something extraordinary. As an object approaches the speed of light, time literally slows down. It is not an illusion, not an optical trick, but a fundamental feature of the universe. As velocity increases, time dilates, stretching like a cosmic elastic that can expand without limit. To grasp the magnitude of this discovery, consider the everyday speeds we experience. When you walk at a normal pace, about 5 kilometers per hour, the effect on time is utterly imperceptible. Your time slows by 1 part in 10 of the 8 number 4, a fraction so tiny that not even the most precise atomic clocks on Earth can detect it. But once you reach 10% of the speed of light, the effect becomes measurable with scientific instruments. Time slows by roughly 0.5%. At 50% of the speed of light, the effect becomes dramatic and unmistakable. A full year for you corresponds to a year and 3 months for someone who remains stationary. At 90% of the speed of light, the effect becomes astonishing. A single year for you equals 2 years and 3 months for someone at rest. Time is visibly stretching before our eyes. Einstein uncovered something even more fundamental: the existence of an absolute speed limit in the universe. 299,792,458 meters per second. This is not merely the speed of light, it is the maximum speed at which any signal, influence, or piece of information can travel. It is the cosmic speed limit encoded in the laws of physics themselves. But here is where the discovery becomes truly extraordinary. As an object approaches this universal limit, time undergoes profound transformations. At 99% of the speed of light, time slows to the point where 1 of your years equals 7 Earth years. At 99.9%, 1 of your years becomes 22 Earth years. And this leads us to the heart of the mystery. What happens at the speed of light? Einstein's equations give an answer that defies all intuition. At exactly the speed of light, the time dilation factor becomes infinite. In practical terms, this means time stops completely. But Einstein also discovered something even more profound. Objects with mass can never reach the speed of light. The energy required to accelerate any massive particle to light speed would be infinite, something the universe simply does not allow. The cosmos contains an inherent protective mechanism preventing any massive object from reaching this temporal boundary. Only massless particles, such as photons, can naturally exist at this universal limit. And for these extraordinary particles, time does not exist. A photon emitted by a star millions of light years away experiences its journey as instantaneous. For the photon, the moment of emission and the moment of absorption in your retina are literally the same instant. This revelation forever changed our understanding of the cosmos and our place within it. Einstein demonstrated that time is not the rigid background Newton imagined, but a dynamic actor in the cosmic drama. Time dances with velocity, stretching and contracting according to the laws of relativity. The elegance of Einstein's discovery lies in its fundamental simplicity. He did not add unnecessary complexity to the universe. Instead, he revealed a deeper order that had been hidden beneath centuries of incorrect assumptions. The cosmos operates according to principles far more beautiful and coherent than we ever dared imagine. Chapter 2: Everyday Speeds and the Measurement of the Impossible. The relativity of time is not an abstract notion reserved for physicists in secluded laboratories. It is a phenomenon that surrounds us continuously, even in this very moment as you read these words. Time dilation is happening in your life right now, real, measurable, and woven into the fabric of existence, although on scales so microscopic that our senses cannot perceive it. But once we turn our attention to the extreme velocities that exist throughout the cosmos, the effects become not only measurable, but profoundly dramatic. Let us begin with something familiar: ordinary life. When you walk down the street at an average pace of 5 kilometers per hour, you are experiencing time dilation. Yes, you read that correctly. Your personal time is flowing slightly slower than the time of someone who is standing completely still. The difference, however, is infinitesimal. About 1 part in 10 is 8 in 8. To put this into perspective, if you walked non-stop for your entire lifetime, the total difference between your time and that of a stationary person would amount to less than 1/millionth of a second. This difference is so incredibly small that even the most advanced atomic clocks ever built, capable of detecting changes on the scale of 1 part in 10 to million-eighth, cannot observe it in everyday circumstances. It is mathematically real, but practically invisible. And yet this tiny effect is the very same mechanism that produces extraordinary distortions of time at velocities near the speed of light. Now let us consider something faster. A modern car cruising down a highway at 120 kilometers per hour undergoes a slightly larger amount of time dilation, though still imperceptible to human senses. After an hour of driving, the difference in time is about 1 part in 10 another 14s. Even if you could maintain that speed for a full century, you would age only about 1 microsecond less than someone standing still. Commercial airplanes flying at cruising altitude reach speeds of around 900 kilometers per hour. At this velocity, the effects of time dilation finally become technically measurable with highly sensitive equipment, although passengers remain entirely unaware. A pilot who spends an entire career flying might accumulate a time difference of a few microseconds compared with someone who never flies at all. But now the story becomes much more intriguing. Satellites orbiting Earth travel at far greater speeds. GPS satellites, for example, circle the planet at roughly 14,000 kilometers per hour. At this velocity, time dilation becomes significant enough to require constant adjustments. The atomic clocks aboard GPS satellites tick about 7 microseconds slower per day due to their orbital speed. 7 microseconds may sound trivial, but consider its practical consequences. GPS signals travel at the speed of light, about 30 centimeters per nanosecond. A 7 microsecond error translates to a positional error exceeding 2 kilometers per day. Without relativistic corrections built directly into the GPS system, your phone would begin showing you kilometers away from your true location within hours. In other words, every time you use your phone to get directions, every time an airplane navigates across continents, every time a ship charts a course across the ocean, you are relying on Einstein's time dilation. Relativity is not academic trivia. It is a practical necessity for modern civilization. Without it, accurate global navigation would simply be impossible. But the GPS story grows even more fascinating. Satellites also experience gravitational effects that make their clocks tick faster than clocks on Earth by about 45 microseconds per day, because gravity is weaker at orbital altitude. This is an effect of general relativity, Einstein's advanced theory that incorporates gravity itself. Combining the slowing from orbital speed, minus 7 microseconds, with the speeding from weaker gravity, plus 45 microseconds, gives a net effect. GPS clocks run 38 microseconds faster per day than clocks on Earth. Those 38 microseconds must be corrected continuously to maintain system accuracy. Now let us move to even higher speeds. The International Space Station orbits Earth at approximately 28,000 kilometers per hour. Astronauts aboard the ISS experience slightly stronger time dilation than GPS satellites. Over a typical 6-month mission, an astronaut ages about 0.007 seconds less than people on Earth. A tiny difference, but real, measurable, and physically meaningful. Russian cosmonaut Sergei Krikalev holds the world record for accumulated time in orbit, 803 days across multiple missions. Because of his time spent traveling at orbital velocity, Krikalev has effectively traveled about 0.02 seconds into Earth's future. He is the most accomplished time traveler in human history, though his temporal journey is measured in fractions of a second. But to observe truly dramatic time dilation, we must consider speeds that represent a significant fraction of the speed of light. Here, Einstein's mathematics shows its full power, and our everyday intuition breaks down completely. At 10% of the speed of light, about 30,000 kilometers per second, the Lorentz factor is approximately 1.005. This means that for every year you experience while traveling at this speed, a person at rest experiences about 1 year and 2 days. A small difference, but clearly noticeable. If you maintained this speed for a decade, you would age about 18 days less than someone on Earth. At 30% of the speed of light, the effect becomes stronger. The Lorentz factor rises to about 1.048. One of your years corresponds to a year and 17 days on Earth. Over a 5-year journey, you would age about 85 days less than your friends and family. At 50% of the speed of light, we enter a range where relativistic effects become truly significant. The Lorentz factor reaches about 1.155. 1 year for you equals nearly a year and 2 months on Earth. If you traveled for a full decade at this speed, 11.5 years would pass back home. You would have effectively traveled a year and a half into Earth's future. At 70% of the speed of light, the effect becomes dramatic. The Lorentz factor is about 1.4. 1 year for you equals a year and 5 months on Earth. A 10-year voyage at this velocity corresponds to 14 Earth years. The differences grow large enough to fundamentally reshape your relationship with the people you left behind. At 80% of the speed of light, the factor climbs to about 1.67. One of your years becomes a year and 8 months on Earth. People you knew as teenagers would return to greet you as fully grown adults after a journey that felt short to you. At 90% of the speed of light, the effect becomes astonishing. The Lorentz factor is roughly 2.29. 1 year of your time equals 2 years and 3 months on Earth. A 5-year mission becomes more than 11 Earth years. Children would be grown, elders would have aged significantly or passed away, and society would have changed in unpredictable ways. At 95% of the speed of light, the factor grows to about 3.2. One of your years corresponds to more than 3 Earth years. The world you return to would be technologically, socially, and culturally transformed. At 99% of the speed of light, we reach extraordinary territory. The Lorentz factor is approximately 7.09. 1 year for you equals more than 7 Earth years. A 10-year mission becomes more than 70 Earth years. You would return to a world that had undergone a complete generational transformation. At 99.9% of the speed of light, the effect becomes almost beyond comprehension. The Lorentz factor reaches about 22.4. One of your years equals more than 22 Earth years. A 5-year voyage becomes more than a century on Earth. You would come home to an era entirely different from the one you left behind. And here is the truly fascinating part. These effects are not symmetrically reflected between observers. If you travel at high speed and return to Earth, you will be the one who has aged less. The accelerations required to turn around and return break the apparent symmetry. This is the core of the famous twin paradox, which we will explore later. The mathematics behind these effects arises from the Lorentz factor, an elegant expression that appears throughout special relativity. It depends solely on one quantity, the ratio of your velocity to the speed of light. As your velocity approaches light speed, the Lorentz factor grows without limit, approaching infinity. And as it grows, time dilation becomes unbounded. But a crucial question arises. If these effects are so dramatic at high speeds, why don't we experience them in everyday life? The answer is simple yet profound. All our everyday velocities are an unimaginably tiny fraction of the speed of light. Even the fastest objects ever built by humanity reach only a minuscule percentage of that cosmic limit. NASA's Parker Solar Probe, the fastest human-made object in history, reached roughly 190 kilometers per second during its closest approach to the Sun. Impressive as this seems, it amounts to only 0.064% of the speed of light. At that speed, the time dilation factor is about 1.0000002, practically indistinguishable from 1, although technically measurable with sufficiently precise instruments. This is why Newtonian mechanics worked nearly perfectly for centuries. Newton was not wrong. His equations are simply an excellent approximation at low speeds. Only when we approach significant fractions of light speed do relativistic effects dominate. At everyday velocities, the corrections are so tiny that they can be ignored without any practical consequence. Chapter 3: The Twin Paradox and the Experiments That Changed Everything. The mathematical implications of special relativity are clear, precise, and mercilessly logical. But the moment we try to translate those equations into the language of real human experience, we run into situations that shake our intuition to the core. Effects that look harmless on paper become genuinely unsettling when we imagine them happening to real people with real lives. The most famous of these scenarios is known as the twin paradox, a thought experiment that has fascinated and unsettled generations of students, scientists, and philosophers ever since Einstein first published his theory and dared to suggest that time itself is not absolute. Imagine two identical twin brothers, born on exactly the same day of the same year. Let us call them Mark and Peter. They grow up together, share a bedroom, fight over toys, celebrate the same birthdays, attend the same school, and accumulate an almost perfectly mirrored set of memories. When they turn 25, they are in perfect health and physically indistinguishable. Same height, same expressions, even the same way of laughing. But then their lives diverge. Peter, who has always dreamed of the stars and spent nights looking at the Milky Way, becomes an astronaut, and he is offered a place on humanity's first interstellar mission. The mission is bold and ambitious, a journey to the star Alpha Centauri, located about 4.37 light-years away from Earth, the closest stellar system beyond our own Sun. Peter's spacecraft is equipped with revolutionary engines capable of accelerating to 95% of the speed of light, a technological marvel representing the pinnacle of human engineering. He accepts without hesitation, fully aware that it will be a long and demanding voyage, but also a unique and historic opportunity to push the frontier of human exploration. Mark chooses to remain on Earth, building a family, pursuing a career, and shaping what we would call a normal life in the familiar gravity of home. Peter departs in his starship. During the first months, the engines push steadily, and he feels the constant pressure of acceleration pressing him into his seat like an invisible hand. Gradually, the ship reaches its cruising speed, 95% of the speed of light. From Peter's perspective inside the cabin, everything appears completely ordinary. Time flows in a familiar, comforting way. He eats his meals, sleeps through his nights, writes in his diary, reads books, watches recorded messages from Earth, and exercises to keep his muscles strong in the artificial gravity of the ship. His clock marks seconds, minutes, hours, and days with perfect regularity, just as it always has. According to Peter's calculations and the readings on the ship's clock, the trip to Alpha Centauri takes about 4.6 years. He arrives in the distant system, carries out his scientific observations for a few weeks, studies the planets and the star's radiation, and then turns the ship around to begin the journey home. Another 4.6 years pass on board during the return flight to Earth. Years that, for Peter, feel long but manageable, filled with routine, maintenance work, and moments of quiet contemplation as he looks out at the stars. When he finally lands, he checks his watch and the mission logs. Approximately 9.5 years have passed since launch. Peter is now 34.5 years old, but as soon as he steps out of the spacecraft and embraces his twin brother, he experiences a profound shock that words struggle to describe. Mark is not 34.5. Mark is 55 years old. The twin, with whom he shared his entire life until the age of 25, now looks like his father, almost as if Peter had skipped ahead into Mark's future. His hair is largely gray, deep wrinkles frame his eyes, and the skin of his face and hands shows the unmistakable softness and looseness of middle age. Mark's children, who were little kids when Peter left, are now young adults with their own concerns and aspirations. Some of them are older than Peter feels he himself should be. What has happened? How can two brothers, born on the same day, no longer share the same age? The answer lies in time dilation. At 95% of the speed of light, the time dilation factor is roughly 3.2. This means that for every year Peter experienced on his ship, about 3.2 years passed on Earth. His 9.5 years in space correspond to about 30 Earth years. Mark has lived those 30 years in full, growing older, facing joys and losses, watching his children grow up, saying goodbye to some loved ones, while Peter has experienced only 9.5 years of personal time. Peter has effectively traveled into Earth's future, not by stepping into a science fiction time machine with flashing lights and spinning gears, but simply by moving at extremely high speeds and then returning home. This is genuine time travel, real and testable, predicted by Einstein's equations and confirmed by experiment after experiment. The story of the twins shows that relativity is not just a set of abstract formulas. It rewrites the timeline of human lives. But now a seemingly troubling question appears, one that has confused many people over the years and fills textbooks with heated discussions. If all motion is relative, why can't Mark claim that he was the one who moved while Peter remained at rest? From Peter's perspective on the ship, doesn't it look as though Earth is the object that raced away and then came rushing back at high speed? And if motion is relative, shouldn't Mark be the one who ages less, depending on who tells the story? This apparent symmetry is precisely why the scenario is called a paradox. At first glance, it seems to contradict a core principle of relativity, that all inertial reference frames are equally valid, and that the laws of physics are the same in each of them. But the resolution of the twin paradox reveals a deeper, more subtle understanding of the theory and forces us to examine carefully what we mean by inertial. The key word is indeed inertial. Special relativity deals specifically with inertial reference frames, frames that move at constant velocity without acceleration in straight lines through space-time. Peter is not in such a frame for the entire mission. He has to accelerate to depart from Earth, decelerate to stop near Alpha Centauri, accelerate again to begin the return leg, and decelerate one last time to land on Earth. The world line of his journey is bent and curved, while Mark's is comparatively straight. These periods of acceleration are crucial. They break the apparent symmetry between Peter and Mark. Mark stays in an essentially inertial frame for the whole duration of the story. Yes, Earth orbits the Sun, and the Sun orbits the galaxy, but those motions are smooth and nearly uniform on the timescale we are considering, and they affect both brothers in almost the same way. Peter, in contrast, undergoes multiple episodes of strong acceleration and deceleration that clearly distinguish his path through space-time from that of his twin. Once acceleration enters the picture, we have stepped into the domain of general relativity, Einstein's more complete theory that incorporates gravity and accelerated frames. General relativity tells us that acceleration is locally equivalent to being in a gravitational field. A rocket accelerating through space is indistinguishable from a room sitting still on a planet, at least for an observer inside. During his acceleration phases, Peter effectively experiences artificial gravity fields, and these fields influence the flow of time in subtle and complex ways, slowing his clock relative to one that remained in a nearly inertial state. It is this asymmetric experience of acceleration that decides, without ambiguity, that Peter is the one who will have aged less. There is no genuine paradox and no hidden flaw in the theory. When the full mathematics of special and general relativity are applied correctly, they predict exactly how much each twin will age, and those predictions match the results of real experiments to extraordinary precision. The twin paradox is not just an elegant thought experiment on paper. Its core idea has been tested in the real world many times, even though we cannot yet send human twins on interstellar journeys. Instead, scientists use extremely precise atomic clocks as twins in carefully designed experiments that track how time passes under different conditions of motion and gravity, turning the planet itself into a vast laboratory. The most famous of these experiments was carried out in 1971 by physicists Joseph Hafele and Richard Keating. They took 4 cesium atomic clocks, the most precise timekeeping devices then available, capable of measuring time intervals on the scale of nanoseconds, and placed them aboard commercial airliners. 2 sets of flights were made around the world, one eastward and one westward, circling the globe much like Peter circled his distant star, but on a far more modest scale. One group of clocks flew east, in the same direction as Earth's rotation. From the point of view of the center of the Earth, these clocks were moving faster because their flight speed added to the rotational speed of the planet. Another group of clocks flew west against Earth's rotation, moving more slowly relative to the planet's center. A third reference clock remained at the U.S. Naval Observatory in Washington, D.C., ticking away quietly as the standard of comparison. Einstein's predictions were clear and quantitative. The eastward flying clocks should run slightly slower because of their higher speed, but slightly faster because they are at higher altitude in a weaker gravitational field. After both effects are combined, the result should be a small net loss of time compared with the ground clock. The westward flying clocks, on the other hand, move more slowly relative to Earth's center, which tends to make them run faster, and they also experience weaker gravity at altitude, which again makes them speed up. Both contributions add in the same direction, so these clocks should show a net gain in time, arriving older than the reference clock. When the planes completed their journeys and the clocks were brought back together and compared with the reference clock in Washington, the result was stunning. The eastward flying clocks had lost about 59 nanoseconds relative to the ground clock. The westward flying clocks had gained about 273 nanoseconds. These may seem like laughably small amounts of time, but at the scale of atomic clocks, they are enormous and unmistakable. These differences were tiny in everyday terms, but they matched Einstein's theoretical predictions with impressive accuracy. The discrepancies between prediction and measurement were within the experimental error bars. The Hafele-Keating experiment provided a direct, dramatic confirmation that time dilation is real, measurable, and quantitatively described by the equations of relativity. It turned an abstract classroom paradox into a concrete, globe-spanning test of how time itself behaves. Yet some of the most spectacular demonstrations of time dilation come not from airplanes or satellites, but from subatomic particles that rain down on Earth from space. Cosmic rays are extremely high-energy particles, mainly protons, that constantly bombard our atmosphere. When these protons collide with atomic nuclei high in the upper atmosphere, they create showers of secondary particles, among them particles called muons. Muons are fundamental and intriguing. They resemble electrons and belong to the same family of particles, leptons, but they are about 207 times more massive. Most importantly for us, they are unstable and radioactive. A muon at rest decays spontaneously into an electron and 2 neutrinos after an average lifetime of only 2.2 microseconds, just 2.2 millionths of a second, a blink of an eye on the subatomic stage. Muons are typically created in the upper atmosphere at altitudes of around 15 kilometers above Earth's surface. They are produced with extremely high velocities, usually around 99.8% of the speed of light. If we calculate how far a muon could travel within its 2.2 microsecond lifetime, even moving almost at light speed, we obtain a distance of roughly 660 meters. Here arises an apparent problem that seems, at first sight, impossible to resolve. Muons are created 15 kilometers above the ground, yet they can travel only 660 meters before decaying. Mathematically, they should disappear long before reaching Earth's surface. We ought to detect almost no muons at sea level. Our detectors should remain almost silent. However, when scientists set up muon detectors at ground level, they measure a huge number of them. In fact, about 10,000 muons pass through each square meter of Earth's surface every hour. Clearly, a large fraction of muons do make it down to the ground. How is that possible? How can particles that die so quickly survive such a long journey? The answer, once again, is time dilation. From our perspective on Earth, the muons are moving at about 99.8% of the speed of light. At that speed, the time dilation factor is roughly 15. This means the internal clock of each muon runs 15 times more slowly than our clocks do. What we see as several tens of microseconds of travel from the upper atmosphere to the ground corresponds, in the muon's own proper time, to only a small fraction of its 2.2 microsecond lifetime. Its internal clock is ticking so slowly relative to ours that it has enough time to survive the full 15-kilometer journey before decaying, just as Peter had enough time to cross interstellar space while decades slipped by on Earth. But there is an even more fascinating way to tell the same story. From the muon's point of view, its lifetime is perfectly normal. Its clock is not slow at all. It still lives, on average, only 2.2 microseconds. So how can it possibly cover 15 kilometers in such a short proper time? Here we must invoke another prediction of special relativity, length contraction. In the muon's frame of reference, it is not its own time that has changed, but the distance it must travel. The 15-kilometer thickness of the atmosphere that we measure on Earth is contracted to about 1 kilometer as seen by the muon. From its perspective, it only needs to cross that much shorter distance in 2.2 microseconds, a perfectly achievable task at 99.8% of the speed of light. Both viewpoints are equally valid and mutually consistent. There is no single correct story written above the others. Relativity teaches that different observers in different frames of reference measure different times and distances, and each description is internally correct within its own frame. What everyone agrees on are the observable facts. For example, the number of muons that reach the surface of the Earth and the decay rates measured in detectors. The explanations differ, but the physical outcome is the same for all observers. This cosmic muon phenomenon is not a classroom curiosity. It is an ongoing, natural experiment that constantly confirms special relativity above our heads every second of every day. Billions of muons are demonstrating time dilation right now while you read these lines, silently writing Einstein's equations into the air. Modern experiments have refined these measurements with astonishing precision. Physicists have measured muon decay rates at different altitudes and at different speeds, confirming Einstein's predictions to within fractions of a percent. Each new measurement strengthens the same conclusion. Time is genuinely relative, and it dilates exactly as the equations of relativity prescribe, no more and no less. Through these experiments and observations, relativity has been transformed from a bold theoretical idea into an experimentally unshakable fact. We are not merely speculating about the nature of time, we are measuring it directly with exquisite accuracy, using clocks, airplanes, satellites, particle accelerators, and cosmic rays as our instruments. And every test, every clock, every unstable particle confirms the same message: time is flexible, elastic, and inseparable from the motion of the observer. Chapter 4: Extreme Cosmic Phenomena and Relativity in Action. The experimental confirmations of time dilation in Earth-based laboratories and with subatomic particles are impressive, but the universe itself operates as a colossal natural laboratory, where relativistic effects unfold on scales far beyond anything we can create artificially. In the most extreme corners of the cosmos, where velocities creep dangerously close to the universal speed limit and gravity warps the very fabric of space-time, relativity is not a minor correction. It is the dominant rule that dictates how reality behaves. Let us begin our journey through these extreme phenomena by exploring pulsars, some of the most fascinating and bizarre objects in the known universe. Pulsars are rapidly rotating neutron stars, the collapsed remnants of massive stars that ended their lives in titanic supernova explosions. Imagine compressing all the mass of the Sun into a sphere only about 20 kilometers across. The resulting density is so unimaginable that a single teaspoon of neutron star matter would weigh roughly 1 billion tons on Earth. These neutron stars spin about their axes at dizzying rates. The fastest pulsar known, designated PSR J1748-2446 AD, rotates 716 times per second. Take a moment to picture that. An object more massive than our Sun, shrunk to a size smaller than a medium city, completing more than 700 full rotations every second. The equatorial surface of such a pulsar moves at about 24% of the speed of light. At this extreme speed, time dilation becomes substantial and measurable. Time on the pulsar's equator flows about 3% more slowly than for a distant, stationary observer. That means if you could somehow stand on the equator of this pulsar for what feels to you like 1 year, an observer watching from far out in intergalactic space would see roughly 1 year and 11 days go by. But pulsars are not only extraordinary because of their rapid rotation, they also possess mind-bendingly strong magnetic fields, trillions of times stronger than Earth's magnetic field. These colossal fields accelerate charged particles to velocities near the speed of light, launching narrow beams of radiation that sweep through space like the beams of a cosmic lighthouse. When these beams cross Earth's line of sight, we detect regular pulses of radiation, giving pulsars their name. The particles accelerated in a pulsar's magnetosphere can reach speeds of 99.9% of the speed of light, or even higher. At such velocities, the time dilation factor is about 22 or more. This means those particles experience time 22 times more slowly than we do. For a particle traveling at 99.9% of light speed, a journey that appears to us to last an entire year feels to the particle like only about 2 weeks. Now let us turn to phenomena even more extreme. Quasars. Quasars are the most luminous and energetic objects in the observable universe. They are active galactic nuclei, powered by supermassive black holes at the centers of distant galaxies. These black holes have masses equivalent to millions or even billions of suns, and consume surrounding matter at ferocious rates. As gas and dust spiral toward the black hole, they heat up to millions of degrees, emitting staggering amounts of radiation. Yet what interests us most here are the relativistic jets that many quasars launch from their poles. These jets are streams of particles and radiation hurled into intergalactic space at velocities that come terrifyingly close to the speed of light. The fastest quasar jets observed move at 99.9% of the speed of light or more. Some have been measured at about 99.995% of light speed. At these incredible velocities, relativistic effects completely dominate the behavior of the material. The time dilation factor for matter traveling at 99.995% of the speed of light is about 100. In other words, time for the particles in these jets flows 100 times more slowly than for us. Consider the implications. From our viewpoint on Earth, we see these jets traverse distances of thousands of light years over periods of thousands or even millions of years. But for the particles inside the jets, this epic voyage across intergalactic space lasts only decades in their internal time. They inhabit a radically different version of the universe, one in which the vast cosmic distances we deem enormous are compressed, and time is slowed almost to a standstill. Quasars also display a fascinating effect known as apparent superluminal motion. When a relativistic jet is pointed almost directly at us, it can appear as though material in the jet is moving faster than light. Of course, nothing actually exceeds the cosmic speed limit. The effect is an illusion produced by geometry and the finite speed at which light itself travels, but it is a direct, observable consequence of motion at extremely relativistic speeds. Here is how it works. Imagine a jet moving toward us at 99% of the speed of light, but not exactly head-on, just a few degrees offset from our line of sight. Material in the jet is almost chasing its own previously emitted light. When a blob of plasma in the jet moves from point A to point B, the light it emits at point B reaches us only a little after the light emitted at point A, because the blob has almost caught up with the earlier photons. From our perspective, the time interval between the arrival of the light from A and the light from B is compressed. When we divide the apparent distance traveled by the apparent time, we find that the blob seems to have moved faster than the speed of light. In some quasars, this apparent speed can be 10 times the speed of light, yet the true velocity is always below the cosmic limit. It is pure relativistic illusion, a trick of perspective and timing. If we wish to explore the most extreme relativistic effects imaginable, however, we must turn our attention to the most extreme objects of all, black holes. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape once it passes the boundary known as the event horizon. Physics near a black hole is so extreme that it stretches human intuition to the breaking point. The supermassive black hole at the center of our own galaxy, the Milky Way, is called Sagittarius A star. It has a mass of roughly 4 million suns. Its event horizon has a diameter of about 24 million kilometers, comparable to the size of Mercury's orbit around the Sun. Yet from the perspective of relativity, The size of the event horizon is not the most interesting feature.
Far more intriguing is what happens to time as you approach that boundary.
Einstein's general relativity predicts that strong gravitational fields slow the flow of time, an effect called gravitational time dilation.
Near a black hole's event horizon, this effect becomes extreme.
Imagine you are watching from a safe distance while a brave, or perhaps very reckless, astronaut approaches the event horizon of a black hole. As the astronaut gets closer and closer, you observe something extraordinary. Their motions appear to slow down. Gestures and movements become sluggish, as though they were wading through invisible molasses. Closer still, their apparent motion slows even more. The light reflected or emitted by the astronaut becomes increasingly redshifted, sliding toward longer wavelengths as photons struggle to escape the intense gravitational field. Eventually, as the astronaut reaches the event horizon itself, you would see them freeze in place. They would appear suspended in time, right on the edge of the black hole. From your external perspective, the astronaut never truly crosses the event horizon. Their image grows dimmer and redder, gradually fading into invisibility, but it always seems to linger just above the horizon. For you, time at the event horizon has effectively stopped. The boundary becomes not only a spatial surface, but a temporal cliff. For the falling astronaut, however, the experience is utterly different. Assuming the black hole is massive enough that tidal forces are not immediately lethal, the astronaut would feel nothing special at the horizon. There is no physical wall, no glowing barrier to mark the crossing. They simply fall. In a finite amount of time, according to their own watch, they cross the event horizon and continue inward toward the central singularity, the region where our current understanding of physics breaks down. This radical disparity between the two perspectives perfectly illustrates the relative nature of time. To the distant observer, the astronaut never crosses the horizon. To the astronaut, the crossing is uneventful and happens in a finite, measurable interval. Both descriptions are equally valid within their own frames of reference. There is no single correct story. Relativity demands that each viewpoint is physically meaningful. Rotating black holes, known as Kerr black holes, introduce phenomena that are even stranger. These black holes drag space-time itself around with them in an effect called frame dragging. Close to a rapidly spinning black hole, it becomes literally impossible to remain at rest relative to distant stars. Space-time is being twisted around the black hole, and anything within a certain region must rotate along with it. There is a zone outside the event horizon of a rotating black hole called the ergosphere, where frame dragging is so intense that even light must orbit in the direction of the black hole's spin. Within the ergosphere, peculiar relativistic effects allow, at least in theory, the extraction of energy from the black hole through a mechanism known as the Penrose process. Although still purely theoretical in practice, it illustrates the bizarre and counterintuitive opportunities that extreme relativity provides. Perhaps the most extreme interplay between black holes and time dilation, however, involves the innermost stable circular orbits around them. For a non-rotating black hole, the innermost stable circular orbit, often abbreviated as ISCO, lies at 3 times the radius of the event horizon. Any closer in, and circular orbits become unstable. Matter either spirals inward to the black hole or escapes outward. An object orbiting at the ISCO of a non-rotating black hole moves at about 50% of the speed of light. At this blistering orbital speed, the time dilation due to motion alone corresponds to a factor of about 1.15. But we must also account for gravitational time dilation, caused by being so deep within the black hole's gravitational well. Together, these two effects mean that time for an object at the ISCO flows significantly more slowly than for an observer far away. For rapidly rotating black holes, the ISCO can lie much closer to the event horizon, and the orbital velocity required can approach an even larger fraction of the speed of light. In these extreme cases, the combined effects of gravitational and kinematic time dilation become enormous. An object orbiting very near the event horizon of a fast-spinning black hole could experience time dilation factors of 10 or more, meaning that its time flows 10 times more slowly than that of a distant observer. The science fiction film Interstellar popularized these concepts with its depiction of a planet orbiting close to a supermassive black hole, where each hour on the planet corresponded to 7 years on Earth. While the movie took creative liberties, the basic physics behind such an extreme time differential is sound. In principle, time dilations of that magnitude are possible near sufficiently massive and rapidly spinning black holes. In these cosmic laboratories, pulsars, quasars, relativistic jets, and black holes, relativity is not an optional add-on. It is the governing language of reality itself. Time bends, slows, stretches, and nearly halts under the combined pressure of enormous velocities and titanic gravitational fields. The universe, in its most violent and spectacular regions, constantly demonstrates that Einstein's insights were not just clever ideas, but accurate descriptions of how spacetime truly behaves. Chapter 5: Consciousness, Technology, and the Frontiers of Temporal Knowledge. The extreme cosmic phenomena we have explored show relativity in action on monumental scales. But these revelations about the nature of time also have deep and practical implications for everyday life, for modern technology, and even for our understanding of consciousness itself. A natural question arises: how does the relative nature of time affect our subjective experience of the world? Can human consciousness adapt to different temporal rhythms? And, more fundamentally, what does it really mean to experience time when we know it is so flexible, so dependent on motion and gravity? Let us begin by examining how time's relativity is already woven into the technology we use daily, often without realizing it. The clearest and most practical example is the Global Positioning System, universally known as GPS. This system, used by billions of people every day to navigate streets, oceans, and airways, depends absolutely on relativistic corrections to function properly. GPS satellites orbit Earth at an altitude of about 20,200 kilometers, completing 2 sidereal orbits per day. At this height, they experience 2 opposing relativistic effects that influence their ultra-precise atomic clocks. First, because of their orbital speed of about 14,000 kilometers per hour, their clocks run slower than clocks on Earth, as predicted by special relativity, by roughly 7 microseconds per day. This is the velocity-based time dilation we have been discussing throughout. At the same time, however, these satellites experience a weaker gravitational field than clocks on Earth's surface. According to Einstein's general relativity, clocks in weaker gravitational fields tick faster. This gravitational effect causes the satellite clocks to gain about 45 microseconds per day. When we combine the 2 influences, the net result is that GPS clocks advance about 38 microseconds per day relative to identical clocks on the ground. 38 microseconds does not sound like much, but GPS signals travel at the speed of light, covering roughly 30 centimeters every nanosecond. A 38 microsecond timing error would accumulate into a positional error greater than 11 kilometers in a single day. Without constant relativistic corrections built directly into the GPS system, your navigation apps would begin telling you that you are many kilometers away from your real position within just a few hours. Accurate navigation would collapse. The engineers who designed GPS had to embed Einstein's equations directly into the satellite's software and hardware. The atomic clocks aboard are deliberately adjusted to run slightly slower than ground-based clocks so that, once the relativistic effects of motion and gravity are included, they remain synchronized with clocks on Earth. Every time you open a map on your phone, every time an aircraft follows a GPS-guided route, every time a ship uses satellite navigation to avoid reefs and coastlines, you are benefiting directly from humanity's understanding of the relativity of time. GPS is only the beginning. Particle accelerators, those gigantic scientific machines where physicists investigate the fundamental structure of matter, depend critically on relativity to operate at all. Inside the Large Hadron Collider, LHC, straddling the border between Switzerland and France, protons are accelerated to about 99.9999991% of the speed of light. At such extreme speeds, the protons experience time dilation factors of roughly 7,500. From our perspective in the control rooms and laboratories, the internal time of those protons passes 7,500 times more slowly than laboratory time. For the particles, each second that we measure corresponds to only a tiny fraction of a millisecond in their own proper time. This enormous time dilation allows them to complete millions of laps around the LHC's 27-kilometer ring before decaying or colliding. Engineers and physicists who design and operate these accelerators must calculate relativistic effects with exquisite precision. The particles' trajectories, the strengths of the magnetic fields that bend them, the timing of the collisions, the design of detectors, all of it must account for the increased relativistic mass of the particles at high speeds and for the way time slows down for them. Without relativity, the beams could not be controlled and the experiments would fail. Now, let us venture into more speculative but equally fascinating territory. How does time dilation affect consciousness and subjective experience? This question lies at the frontier where physics, neuroscience, and philosophy intersect. We know that physical time is relative, but what does that imply for the way we feel time passing? Human consciousness seems to operate with its own internal sense of time. Everyone has experienced moments in which subjective time appears to accelerate or slow down. Instants of extreme danger or emotional intensity are often remembered as if they unfolded in slow motion. Long periods of boredom can feel endless, while moments of joy or deep engagement seem to vanish in an instant. These effects are psychological, rooted in how our brains process, filter, and store information. But they raise intriguing questions. If an astronaut travels at relativistic speeds, their brain, being a physical system made of atoms and molecules, undergoes time dilation along with the rest of their body. Neuronal processes slow down relative to an outside observer, but for the astronaut, everything feels perfectly normal. Thoughts, emotions, sensations, and memories unfold at their usual pace. Their heartbeat, inner monologue, and perception of duration all remain internally consistent. This suggests that conscious experience of time is inherently tied to the observer's own reference frame. There is no universal, objective, master clock of lived experience. Your perception of time is always anchored to your state of motion and your position in gravitational fields. This is a profound insight into the nature of both time and consciousness. Our inner sense of duration is as relative as the physical clocks we build. Imagine an advanced civilization that has mastered routine travel at velocities close to the speed of light. Individuals in such a society could choose to experience time at different effective rates, depending on their goals and desires. Someone who wants to witness the completion of a long-term megastructure or the evolution of a star system could embark on high-speed voyages, effectively leaping forward into the future of their home world. Others might prefer to remain in more slowly moving habitats, to live their lives in step with friends, family, and local events. The ability to tailor one's personal temporal trajectory would have enormous social and psychological consequences. Relationships would become complex when people can experience radically different amounts of aging over the same span of external time. A parent who leaves on a relativistic exploration mission might return to find that their children have grown older than they are. Friends who part ways could reunite decades later, having lived through very different durations of subjective time. This is not purely science fiction speculation. Astronauts aboard the International Space Station already experience tiny versions of this effect. After a 6-month mission in orbit, an astronaut has aged about 0.007 seconds less than people on Earth. The difference is far too small to be felt, but it is real and measurable, a literal, if microscopic, journey into Earth's future. As humanity begins to consider more ambitious space missions, journeys to Mars, to the moons of Jupiter and Saturn, and eventually to other star systems, relativistic and temporal effects will grow more important. Mission planners will have to address not only the physical logistics of fuel, life support, and radiation, but also the temporal and psychological consequences for the crew. Even a mission to Mars with current technology taking about 9 months each way poses significant temporal challenges. The spacecraft's velocity is far too low for noticeable relativistic time dilation, but the increasing delay in communication leads to a kind of psychological time distortion. When Mars and Earth lie on opposite sides of the Sun, radio signals can take up to 22 minutes each way. Conversations become slow, fragmented, and asynchronous. The crew's experience of life on Earth becomes more and more delayed, as if they were watching reality through a slowly updating window. Now consider missions that reach much further. A voyage to Alpha Centauri, 4.37 light-years away, would require relativistic speeds to be completed within a human lifetime. If we could someday build a ship capable of traveling at 95% of the speed of light, the one-way trip would take about 4.6 years according to the ship's clocks, while more than 14 years would pass on Earth. A round trip would last about 9.5 years for the astronauts, but more than 28 years for the people they left behind. This temporal disparity would create a unique psychological burden. The crew would embark knowing that while they experience less than a decade of life, nearly 3 decades will pass for their families, friends, and the rest of human civilization. Returning home would mean stepping into a future world in which politics, culture, technology, and personal relationships have all advanced without them. It is a very real form of time travel, entirely consistent with known physics, but emotionally and ethically challenging. The ethical implications of such missions are significant. Is it fair to ask explorers to accept such extreme temporal dislocation? How will societies support individuals who return as temporal outsiders, young in body, but separated by decades of change from those they love? How will families, partnerships, and communities adapt to a world in which travel does not just change where you are, but when you are? Returning to the present, let us look at another frontier, where time's relativity is pushing the edge of human knowledge. Fundamental research in physics. Scientists continue to perform increasingly precise experiments to test relativity's predictions and to search for tiny deviations that might point beyond Einstein's framework. Modern optical clocks are so precise that they can detect time differences caused by height variations of just 1 centimeter. These devices use atomic transitions in the optical part of the electromagnetic spectrum, achieving accuracies on the order of 1 part in 10 to the 1784. At this level, you can literally measure the gravitational time dilation between your feet and your head if you stand upright for long enough. Such ultra-precise clocks are opening entirely new avenues of investigation. Researchers use them to search for possible drifts in the fundamental constants of nature over time, to detect gravitational waves using timing methods that complement existing detectors, and to probe the interface between quantum mechanics and general relativity in regimes where both theories are simultaneously relevant. One particularly exciting frontier is the development of ultra-precise space clocks. The European Space Agency, for example, has launched missions such as ACES, Atomic Clock Ensemble in Space, designed to test relativity with unprecedented accuracy. These experiments may one day reveal tiny discrepancies in Einstein's predictions, subtle hints of new physics waiting beyond our current theories. Physicists are also exploring the quantum limits of time measurement. Quantum mechanics imposes fundamental constraints on how precisely we can measure time without significantly disturbing the systems we are observing. Understanding these quantum limits of timekeeping is essential both for basic science and for future technologies, from quantum communication networks to ultra-secure navigation systems. Another active area of research involves searching for possible modifications to special relativity at extremely high energy scales. Some candidate theories of quantum gravity suggest that space-time might become granular or foamy at unimaginably small distances, near the Planck length of about 10⁻³ meters. At such scales, the very notion of smooth space-time may break down, and the familiar rules of relativity might require subtle corrections. To look for hints of such effects, scientists study ultra-high energy cosmic rays, analyze the light from distant gamma-ray bursts for slight energy-dependent delays, and design laboratory experiments with ever-increasing sensitivity. So far, no deviations from special relativity have been found. The theory continues to pass every test with extraordinary precision. But the search itself defines the cutting edge of our quest to understand time and space-time at their deepest levels. Taken together, these technological, experimental, and conceptual frontiers reveal a profound truth. Time is not a rigid, universal backdrop. It is dynamic, relative, and intimately intertwined with matter, energy, gravity, and consciousness. Every GPS fix on your phone, every beam of particles in an accelerator, every tick of an optical clock, and every astronaut in orbit confirms the same conclusion. The river of time does not flow the same way for everyone. It bends and stretches with motion and gravity, and our understanding of it is still evolving. Chapter 6: Future Frontiers and the Quest for New Temporal Horizons. The journey we have taken through the nature of time has carried us from Einstein's revolutionary equations to the furthest, most extreme edges of the observable cosmos. We have seen time stretch for subatomic particles, slow to a crawl near supermassive black holes, and quietly embed itself in the technologies we rely on every single day. Yet our understanding of time is anything but complete. In many ways, we stand at the threshold of new discoveries that could expose aspects of time that not even Einstein imagined. The future frontiers of temporal research promise revelations powerful enough to transform our understanding of reality once again. Let us begin with one of the most promising avenues for future exploration: the detection of gravitational waves with unprecedented precision. Gravitational waves are ripples in the fabric of space-time itself, predicted by Einstein in 1916, but not directly detected until 2015 by the LIGO Observatory. These waves are generated by violent cosmic events, such as the mergers of black holes or neutron stars. As they pass through space, they literally stretch and squeeze space-time, changing the distances between objects in ways that are unimaginably small, yet still measurable. Today's gravitational wave detectors, LIGO, Virgo, and CAGRA, are feats of engineering capable of sensing changes in length far smaller than a fraction of a proton's diameter. But the next generation of detectors aims to go even further. The space-based observatory LISA, short for Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will consist of 3 satellites forming a gigantic triangle in space, with sides 2.5 million kilometers long. This configuration will allow scientists to detect gravitational waves at much lower frequencies than ground-based detectors can reach, opening an entirely new window on the gravitational universe. LISA will be able to detect gravitational waves from mergers of supermassive black holes in the centers of distant galaxies, events that occurred billions of years ago. More importantly for our exploration of time, LISA will provide exquisitely precise tests of general relativity in regimes we have never probed before. Gravitational waves carry detailed information about the structure of space-time itself, and measuring them with extreme accuracy will allow us to search for subtle deviations from Einstein's predictions that might point toward new physics. One particularly fascinating possibility is that gravitational waves could reveal quantum effects in the structure of space-time. Quantum mechanics and general relativity are the 2 most successful theories in all of physics, yet in their current forms they are fundamentally incompatible. Quantum mechanics describes particles and fields on microscopic scales, while general relativity governs gravity and the geometry of spacetime on cosmic scales. For decades, physicists have been searching for a unified theory of quantum gravity that reconciles these 2 seemingly contradictory descriptions of reality. Gravitational waves might provide the first experimental clues about how quantum gravity actually works. Some theories predict that the quantum structure of spacetime should produce tiny corrections in the way gravitational waves propagate, effects that might become detectable with sufficiently sensitive detectors. Observing such signatures would be revolutionary, on par with Einstein's original realization that time itself is relative. Another exciting frontier involves experiments designed to explore the intersection of quantum mechanics and relativity in carefully controlled laboratory systems. Physicists are developing techniques to create quantum states of macroscopic objects, objects large enough for gravitational effects to matter, yet small and isolated enough to maintain quantum properties. These hybrid systems could allow us to study how time behaves when both quantum and relativistic effects are simultaneously significant. One particularly intriguing proposal involves placing an atomic clock into a quantum superposition of being at 2 different heights. According to general relativity, the clock at the higher altitude should tick faster than the one at the lower altitude because of gravitational time dilation. According to quantum mechanics, however, if the clock is in a superposition of both locations, it should simultaneously experience both ticking rates. What happens when we finally measure the clock? Does its state collapse into one of the 2 possible time rates? Or does something even stranger occur, something we do not yet have language for? These experiments are not yet technologically feasible, but rapid advances in quantum control and precision timekeeping are bringing them closer to reality. Their results could reveal entirely new aspects of time's nature, features we currently do not even understand well enough to formulate as clear questions. In exploring these systems, we would be venturing into truly unknown territory at the intersection of our 2 most fundamental theories. The optical clocks mentioned earlier are also opening radically new possibilities for fundamental physics. These clocks are now so precise that they can detect the relativistic effect of simply moving a clock vertically by 1 centimeter. This extraordinary sensitivity makes them ideal tools for searching for subtle variations in the fundamental constants of nature, Some theories beyond the standard model of particle physics predict that constants such as the electron's mass or the fine structure constant might change extremely slowly over cosmic time. Ultra-precise optical clocks could detect such changes if they exist at all. Another fascinating application of these clocks lies in relativistic geodesy, the study of Earth's shape and gravitational field using relativistic effects. Because time flows at slightly different rates at different altitudes and at different locations in Earth's gravitational field, a global network of ultra-precise clocks could map the planet's gravitational potential with unprecedented resolution. This would have practical applications in geophysics, allowing us to detect subtle changes in the distribution of mass inside Earth, to monitor tectonic plate motions more accurately, and even to anticipate volcanic eruptions or earthquakes by detecting tiny precursor changes in gravity. Perhaps the deepest implications of our evolving understanding of time, however, concern fundamental cosmological questions about the origin and ultimate fate of the universe itself. Time, as we currently understand it, appears to have begun with the Big Bang roughly 13.8 billion years ago. Before the Big Bang, the very concept of time as we know it may simply not apply. This raises profound philosophical questions about the nature of time and existence. Some cosmologists have proposed models in which time is emergent, arising from something more fundamental at the quantum level. In such models, time is not a basic ingredient of reality, but a property that emerges from deeper processes as the universe evolves. If this view is correct, then our present understanding of time, even including all of Einstein's relativity, might be only an approximation to a deeper truth. Other physicists have explored the possibility that time is cyclical on cosmological scales. In cyclic universe models, the Big Bang is not an absolute beginning, but merely the latest in an endless series of expansion and contraction cycles. Time would extend infinitely into the past and the future, though each cycle might be separated from the others in ways that make the transfer of information between cycles impossible. These models can resolve certain conceptual issues associated with a single Big Bang, but they introduce challenging new questions of their own. Dark energy, the mysterious component that is accelerating the universe's expansion, also carries profound implications for the far future of cosmic time. If dark energy continues to dominate the universe's evolution, then all distant galaxies will eventually recede beyond our cosmological horizon. In an unimaginably distant future, perhaps hundreds of billions of years from now, the observable universe might consist only of our local group of galaxies, with everything else forever hidden beyond an ever-expanding cosmic boundary. In that remote future, the experience of cosmic time would be radically different from ours. Most stars would have burned out. Many black holes would have evaporated through Hawking radiation. The universe could become a vast, cold, and sparse place, filled mostly with isolated particles separated by unthinkable distances. In such a cosmos, what would time even mean? Would time still exist in any meaningful sense in a nearly empty universe with scarcely any events to mark its passage? Questions like these push us toward even more speculative proposals about the nature of time. Some physicists have suggested that time might not be fundamental at all. In certain approaches to quantum gravity, particularly loop quantum gravity, time is thought to emerge from more basic relationships among quantum events, rather than existing as a pre-established dimension through which those events evolve. Italian physicist Carlo Rovelli has argued that the time we experience is a thermodynamic property, arising from our macroscopic perspective on systems with enormous numbers of particles. At the most fundamental, microscopic level, the laws of physics are largely time-symmetric, showing no intrinsic preference for past over future. The arrow of time we experience appears only because we are complex macroscopic systems interacting with our environment in ways that increase entropy. From this viewpoint, the sensation of temporal flow, that visceral feeling that time moves from past to future, might be fundamentally illusory, a byproduct of our status as entropy-producing systems within a universe whose overall disorder is increasing. At the deepest level, all moments could coexist equally within a four-dimensional space-time block, with no objective, moving present slicing reality into past and future. If time is emergent or illusory at the most fundamental level, we are forced to confront unsettling questions about causality and free will. If all moments exist equally, and the flow of time is merely a subjective impression, in what sense do our present decisions cause future events? Do notions like choice, agency, and responsibility still make sense in a block universe where past and future are equally fixed? These are profound philosophical issues that remain open today, with physicists, philosophers, and neuroscientists all contributing different perspectives. There is no consensus on the answers. Indeed, some of these questions may lie beyond what physics alone can ever fully resolve. They may involve aspects of conscious experience that, while correlated with physical processes, cannot be entirely reduced to them. Future technologies may also let us explore time's relativity in entirely new ways. If humanity develops much more advanced space travel capabilities, especially propulsion systems capable of reaching substantial fractions of the speed of light, relativistic effects will become not only measurable, but experientially significant. The travelers themselves. This would force us to develop new social norms and legal frameworks to handle temporal disparities between spacefarers and those who remain on Earth. Imagine a future era in which interstellar missions are routine. Travelers embarking on such journeys would know that they are deliberately choosing to leap into Earth's future. They might depart, leaving behind young families, and return to find that several generations have passed. How would this reshape social and family structures? Would distinct cultures emerge, one for those who roam the stars, and another for those who stay planet-bound? Could a civilization maintain cultural cohesion when different segments of its population experience time at radically different rates? These are not merely distant hypotheticals. As humanity seriously contemplates expanding beyond Earth, to Mars, and eventually to more distant destinations, we will have to confront the practical realities of relativistic effects, even if they are modest at first. Every step toward becoming a truly spacefaring species will compel us to think more carefully about the nature of time, its role in our lives, and how it shapes the future of our civilization. In the end, the future frontiers of temporal research are not only about better equations or more delicate instruments. They are about redefining what it means to inhabit a universe where time is not a universal stage, but an active, malleable participant in every story. As our clocks grow more precise, our telescopes more sensitive, and our spacecraft more capable, we are gaining the power not just to measure time with unprecedented fidelity, but to engineer our trajectories through it. The choices we make as individuals, as a species, and as a technological civilization will determine how we navigate these new temporal landscapes. Whether we use this understanding to retreat into comfortable illusions or to confront the full, sometimes unsettling truth about our place in space-time will be one of the defining questions of the coming centuries. Whatever the outcome, one conclusion is already unavoidable. Time is not a simple backdrop we move through. It is a rich, structured, and deeply layered aspect of reality, entwined with gravity, motion, quantum phenomena, information, and life itself. To study time is to study the ultimate architecture of the universe, and, at the same stroke, the ultimate architecture of our own existence. Chapter 7. Final Reflections. Our Place in a Temporal Cosmos. We have reached the end of an extraordinary journey through some of the deepest mysteries of time, starting from Einstein's revolutionary equations and traveling all the way to the most extreme edges of the observable universe. Now, in this final part of our exploration, it is time to step back and reflect on what all of this truly means for us as conscious beings living in a cosmos where time itself can slow down, stretch, and even come to a complete halt in ways that utterly defy everyday intuition. What does this understanding teach us about our position in the universe? And how does it transform the way we see existence itself? The first profound lesson that emerges from our journey is the astonishing plasticity of time. For thousands of years, humanity assumed that time was absolute, universal, and unchanging. That assumption felt so obvious, so self-evident, that questioning it would have seemed absurd. Yet Einstein demonstrated that this deeply ingrained intuition was wrong. Time is not the rigid, featureless backdrop we once imagined. It is a dynamic player in the cosmic drama, able to stretch, contract, and, at the ultimate limit of light speed, freeze entirely. This realization about the malleable nature of time affects everything, from the devices we casually use every day to the grandest scales of cosmic evolution. The global positioning systems that guide our journeys rely on precisely computed relativistic corrections. Without understanding that time flows at different rates for satellites in orbit and receivers on Earth's surface, accurate navigation would be impossible. Every time you open your phone to get directions, you are directly benefiting from Einstein's discovery that time is relative. Yet the implications go far beyond practical technology. Recognizing that time can completely stop at the speed of light has pushed us to contemplate forms of existence that lie far outside our ordinary temporal experience. Photons, the fundamental particles of light that constantly bathe us, reveal that there exists a mode of being where ideas like before, after, past, and future lose all meaning. For a photon, the moment it is emitted from a distant star and the moment it is absorbed in your retina are not two distinct events separated by years of travel. They are the same, single, timeless instant. This atemporal perspective illuminates just how contingent and specific our own temporal experience really is. We, as beings made of matter, are fundamentally bound to the flow of time. We cannot escape temporality because we are composed of particles with mass, and particles with mass can never reach the speed of light. We are fated, or perhaps privileged, to experience time continuously, moment after moment, never stepping outside the stream. Yet now we know that our experience is not the only possible way for being to exist in the cosmos. We have seen that the universe itself carries out relativistic experiments on scales that vastly exceed anything we can replicate on Earth. Pulsars spin hundreds of times per second, their equators racing along at a quarter of light speed. Quasar jets tear through intergalactic space at 99.8% of the speed of light, crossing thousands of light years while experiencing only decades of internal time. Black holes create horizons where time literally halts from an external point of view, forming absolute boundaries between different regimes of temporal existence. All these phenomena confirm that we live in an inherently relativistic cosmos, where Einstein's seemingly strange predictions are vindicated again and again on monumental scales. The twin paradox has shown us that simultaneity itself is relative, that there is no universal now that links distant events. This relativity of simultaneity challenges our most basic assumptions about shared experience. When you gaze at the night sky, The stars you see are not all existing in the same present moment. The light from some has been traveling for years, decades, centuries, or even millennia before reaching your eyes. You are literally seeing the past, a patchwork of events that occurred at different times but appear together only because of differing distances and the finite speed of light. This realization reveals that reality is far stranger and more flexible than our evolutionary intuitions prepared us to grasp. Our brains evolved to navigate a world of low speeds and weak gravitational fields where relativistic effects are utterly negligible. It is no wonder that relativity feels counterintuitive. Our instincts were never tuned for velocities near light speed, or for the brutal gravity near black holes. Yet through reason, mathematics, and careful experiment, we have managed to transcend these evolutionary limits and understand aspects of reality that lie completely outside direct human experience. The experiments that confirm time dilation, from cosmic ray muons to atomic clocks aboard airplanes and satellites, demonstrate that relativistic effects are not abstract curiosities. They are concrete physical realities that shape the behavior of particles, atoms, instruments, and entire systems. Relativity is not an optional interpretation of the universe. It is a precise, experimentally verified description of how the cosmos actually behaves. Ignoring it is not an option if we wish to understand reality or build technologies that rely on precise timekeeping. Our exploration of consciousness at the edge of lightspeed has led us to ask what experience itself really is. We have seen that consciousness may be more temporally flexible than we usually assume, capable of operating across a range of temporal regimes, from ordinary, day-to-day durations to extreme relativistic conditions where time slows dramatically. An astronaut traveling near light speed would experience their own consciousness as completely normal. Thoughts, emotions, and perceptions would flow at the usual pace. Only upon returning and comparing clocks would they discover that they have lived through less time than those who stayed behind. This observation raises deep philosophical questions about the nature of conscious experience and its relationship to physical time. Is consciousness fundamentally temporal? Does it require a flowing sequence of moments? Or could some form of consciousness exist in genuinely atemporal states? These questions remain open, perched at the intersection of physics, neuroscience, and philosophy of mind. But the fact that we can articulate them coherently at all is itself a remarkable achievement of human understanding. The future frontiers of temporal knowledge promise revelations that may prove even more astonishing. Next-generation gravitational wave detectors like LISA will explore the gravitational universe with unprecedented sensitivity, potentially revealing quantum effects in the very structure of spacetime. Ultra-precise optical clocks already detect height differences of a single centimeter by measuring relativistic time shifts, opening entirely new possibilities for geodesy, fundamental physics, and the search for variations in supposedly constant physical parameters. Experiments designed to probe the intersection of quantum mechanics and general relativity may uncover aspects of time that not even Einstein considered. Placing atomic clocks into quantum superpositions at different gravitational potentials could force us to reconcile quantum time and relativistic time in entirely new ways. The outcomes of such experiments might be as revolutionary as Einstein's original discoveries more than a century ago. Perhaps most striking of all is how this understanding of relative time transforms our view of our place in the cosmos. We are no longer passive inhabitants of a universe governed by a single, absolute, unchanging time. Instead, we are active participants in a cosmic symphony where time itself is one of the principal instruments, speeding up, slowing down, and sometimes stopping altogether depending on local physical conditions. Our velocity, our position in gravitational fields, our path through space-time, all these factors shape our unique temporal experience. This insight grants us a genuinely cosmic perspective. We can appreciate at the same time both the familiar temporal flow of everyday life and the atemporal realities that exist at the limit of light speed. We can contemplate the finite, fragile duration of our individual lives while also recognizing the timeless eternity experienced by photons that continually connect events separated by immense spans of space and time, yet merge them into single, instantaneous acts from their own viewpoint. The deep beauty of this dual perspective lies in how it allows us to appreciate the extraordinary temporal richness of the universe. We can cherish the preciousness of each fleeting moment we live, knowing that these moments are irreversible and finite from our perspective, while also understanding that there exists a mode of being in which all moments are eternal and simultaneous, where the boundaries between past, present, and future dissolve completely. This understanding also teaches scientific and philosophical humility. No matter how powerful our mathematical tools and abstract reasoning become, we remain essentially temporal beings. We can grasp, with equations and thought experiments, the atemporality of photons and the structure of space-time, but we will never be able to experience that atemporality directly. This limitation reminds us that there will always be aspects of reality that lie beyond the reach of direct subjective experience. Regions of existence we can describe conceptually, but never inhabit. At the same time, this limitation makes our conceptual reach all the more remarkable. Despite being permanently confined to flowing time, despite never escaping the endless sequence of one moment after another, we have learned to understand timeless aspects of reality through abstract thought, mathematics, and careful observation. This is a profound kind of transcendence that does not require us to abandon our physical constraints, but instead invites us to expand our understanding far beyond them. The relativity of time also offers important lessons about the fundamental nature of information in the cosmos. Photons act as atemporal messengers, linking events separated by vast stretches of space and time. From external perspectives, they carry information across light years over long durations. From their own perspective, this transmission is instantaneous, without duration. This reveals that information can operate under temporal rules that extend far beyond our everyday notions of communication and causality. Our exhaustive exploration has revealed that time is both stranger and more elegant than anyone could have imagined before Einstein. The same mathematical equations that describe tiny, almost imperceptible effects in Earth-based laboratories also govern the most violent and spectacular phenomena in the entire universe. This extraordinary universality strongly suggests that we have uncovered something genuinely fundamental about the deep architecture of reality. Not just a convenient approximation, but a profound truth about how the universe is structured. Understanding the speed of light as an absolute insurmountable barrier teaches us that there are fundamental limits in the cosmos that no amount of engineering, technology, or energy can overcome. These limits are written into the geometry of space-time itself. They are not technical challenges to be solved, but absolute boundaries between different possible modes of existence. No matter how advanced a civilization becomes, it will never accelerate a massive object to light speed, because doing so would require infinite energy, an absolute physical impossibility. Yet perhaps the most transformative lesson of our entire journey is the recognition that we are living at an extraordinary, privileged moment in cosmic history. We are among the first generations of humans to truly comprehend the relative nature of time, to glimpse the atemporality that exists at light speed, and to consciously recognize our unique position as living bridges between the temporal and the timeless. This insight makes us heirs to an extraordinary scientific tradition that began with Einstein's revolutionary vision and continues to expand toward frontiers we can barely imagine. Each new discovery about the fundamental nature of time brings us a little closer to a richer, more nuanced understanding of our place in a cosmos that is simultaneously stranger, more beautiful, and more coherent than our ancestors could ever have dreamed. At Deep Space Comm, we continue to explore these deep mysteries that reveal the true nature of our universe. If this long journey through the temporal secrets of the cosmos has awakened in you even a fraction of the fascination that drives us to contemplate these scientific wonders, then you are warmly invited to join future explorations where rigorous science meets genuine awe and profound reflection. We are natural, inevitable, temporal travelers, moving inexorably into the future at the fixed rate of 1 second per second, yet endowed with the extraordinary and unique capacity to understand that other, radically different modes of temporal motion are possible, including the ultimate limit at which time itself ceases entirely. This dual awareness grants us a genuinely privileged vantage point in the cosmos. We are the only known entities capable of intellectually appreciating both the temporality we directly experience and the atemporality we can grasp only through mathematics and theory. In this final moment of reflection, consider that every single photon of light that has reached your retina while you have been reading and pondering these ideas has experienced its entire journey, from its source to your eyes, as a single, absolutely instantaneous, timeless event. While you have experienced a duration filled with thought and interpretation, the photons that enabled your vision have existed only in an eternal present, without beginning or end in time. This striking juxtaposition of temporality and atemporality, occurring simultaneously in your act of reading, perfectly illustrates the extraordinary richness of the cosmos in which we are fortunate enough to exist, to feel, and to contemplate. Time can stop completely at the speed of light, yet our human capacity for wonder at this fact transcends any particular temporal frame. We are, in a very real sense, extraordinary creatures living in an even more extraordinary universe, capable of uncovering truths about reality that would seem indistinguishable from magic to any observer lacking our scientific and mathematical tools. This is our inheritance as conscious beings in a relativistic cosmos, and this understanding should fill us both with humility in the face of the vast unknown and with a quiet, justified pride in how much we have already managed to comprehend.